What if we could journey to distant stars in the blink of an eye, traversing the vast cosmic ocean with unimaginable speed? The very notion of traveling faster than light has captivated the human imagination for generations. Could such a feat be possible? Or is it destined to remain a tantalizing dream? The speed of light, a staggering 299,792,458 meters per second, stands as an unbreachable barrier. But what if there were a way to circumvent this cosmic speed limit? Imagine a future where interstellar voyages are no longer constrained by time. Gravity, the invisible force that binds us to the Earth, governs the motion of celestial bodies and shapes the very structure of the universe. It's a force we experience every day, yet its true nature remains a profound mystery. According to Einstein's general theory of relativity, gravity is not a force at all, but rather a curvature of spacetime. Massive objects create distortions in spacetime, much like a bowling ball on a trampoline. This revolutionary insight opened up new scientific possibilities. Gravity, the invisible force that shapes the cosmos, governs the motion of celestial objects. From the orbits of planets around stars to the dance of galaxies within clusters, gravity orchestrates a cosmic ballet. It's a force that operates across vast distances, binding the universe together. Imagine our solar system held in orbit by the sun's gravity. Each body follows a path, dictated by its mass and distance. The inner planets whip around the sun while the outer gas giants move leisurely. The sun's gravity extends far, influencing stars within the Milky Way. The Milky Way rotates like a pinwheel held by the gravity of its stars, gas and dust. Galaxies cluster together, forming vast cosmic structures. These clusters, containing hundreds of galaxies, are held by gravity. Gravity's influence is not confined to space. It's a force we experience every moment of our lives, right here on Earth. From standing on the ground to astronauts in orbit, gravity shapes our experiences. Consider an apple falling from a tree. Newton used this observation to develop his law of universal gravitation. The same force governs the motion of the moon and planets. Gravity keeps our feet on the ground and gives objects their weight. Weight measures the force of gravity on an object's mass. Gravity shapes Earth's atmosphere, oceans and continents. For centuries, Newton's law of universal gravitation explained gravity on Earth and in the heavens. But in the early 20th century, Albert Einstein revolutionized our understanding with his theory of general relativity. Einstein proposed that gravity is a curvature of spacetime, the very fabric of the universe. Imagine a bowling ball on a trampoline. The ball's weight causes the trampoline to sag. Similarly, massive objects create distortions in spacetime. These distortions are what we perceive as gravity. Einstein's revolutionary insight that gravity is a curvature of spacetime opened up a Pandora's box of possibilities, challenging our fundamental understanding of the universe and hinting at the potential for manipulating this fundamental force. If gravity is not a force but a property of spacetime, could we potentially manipulate spacetime itself to achieve seemingly impossible feats like traveling faster than light? The concept of faster-than-light travel, once relegated to the realm of science fiction, suddenly seemed less outlandish in the light of Einstein's theories. If we could find a way to manipulate space-time, to warp and bend it to our will, perhaps we could find shortcuts through the cosmos, collapsing the vast distances between stars and galaxies. This tantalizing possibility has captivated the imaginations of physicists and science fiction writers alike, inspiring countless stories and theories about wormholes, warp drives, and other exotic concepts that could potentially allow us to break free from the constraints of conventional space travel. However, manipulating space-time is no easy feat. It would require unimaginable amounts of energy and a mastery of physics beyond our current understanding. The challenges are immense, but the potential rewards are even greater. If we could unlock the secrets of space-time manipulation, we could unlock a new era of space exploration, venturing into the cosmos in ways we can only dream of today. Imagine yourself aboard a sleek, futuristic spacecraft embarking on a journey to a distant star system. The hum of the engines fills the air as you settle into your acceleration couch. Ahead lies a voyage that will push the boundaries of human ingenuity. As the countdown reaches zero, the spacecraft surges forward. It's a subtle shift in the fabric of space-time itself. You're riding a wave of warped gravity, traveling faster than light. The stars distort and stretch, a mesmerizing display of cosmic contortions. Outside, the universe rushes by in a blur of streaking stars and swirling nebulae. The ability to manipulate gravity for faster-than-light travel would represent a paradigm shift in our understanding of the universe and our place within it. It would shatter the barriers of time and distance, opening up a realm of possibilities that currently reside solely within the realm of science fiction. Imagine the scientific discoveries that await as we unlock the secrets of gravity, unraveling one of the most fundamental forces in the cosmos. With warp drive technology at our disposal, we could explore the Milky Way galaxy with unprecedented freedom, visiting nearby star systems in a matter of days or weeks instead of centuries or millennia. We could study distant planets up close, searching for signs of life beyond Earth and unraveling the mysteries of planetary formation. We could even venture beyond our own galaxy, journeying to distant corners of the universe currently hidden from our view. The vast cosmic ocean, teeming with billions of galaxies, each containing billions of stars, would become our playground, ripe for exploration and discovery. The implications for humanity would be profound. The ability to travel between stars would ignite a new era of space exploration and colonization, expanding our presence beyond Earth and diversifying our species' portfolio on a cosmic scale. It would foster collaboration and resource sharing among distant worlds, promoting peace and understanding on an interstellar level. The prospect of faster-than-light travel fueled by gravity manipulation is a testament to our desire to explore the unknown, to push the boundaries of human experience and unravel the mysteries beyond our celestial doorstep. Imagine setting foot on a planet orbiting a distant star, its alien landscape bathed in the warm glow of a foreign sun, the air filled with sounds of exotic life forms and a sky ablaze with dazzling constellations. Discovering extraterrestrial life would alter our understanding of our place in the universe. Studying other planets could provide insights into Earth's climate and sustainability. The dream of manipulating gravity for faster-than-light travel may seem like a distant fantasy, but history has taught us that what seems impossible often becomes reality. Just as the Wright brothers paved the way for space travel, our current forays into gravity manipulation could unlock interstellar voyages. The path will be fraught with challenges. We need new materials and energy sources and a deeper understanding of the universe's laws. The dream of warp speed may lie generations ahead, but the journey begins now. The universe awaits, and the possibilities are boundless. The tantalizing idea of faster-than-light travel has captured imaginations, inspiring dreams of exploring distant galaxies and encountering alien civilizations. The warp drive proposes to circumvent the speed of light by manipulating space-time itself. Popularized by Star Trek, the warp drive has become a subject of serious scientific inquiry. Physicists and engineers explore the theoretical underpinnings of warp drive technology. To comprehend the concept of a warp drive, we must first delve into the mind-bending realm of Einstein's general theory of relativity. According to Einstein, gravity is not a force acting at a distance, as Newton had proposed, but rather a curvature of space-time, the very fabric of the universe. Imagine a bowling ball placed on a trampoline. The bowling ball's mass causes the trampoline's fabric to sag, creating a dip. Similarly, massive objects like stars and planets create distortions in space-time, much like the bowling ball on the trampoline. These distortions are what we perceive as gravity. The warp drive concept hinges on the idea that if we can manipulate the curvature of space-time, we can create shortcuts through the cosmos, essentially altering the geometry of space itself. Imagine folding a piece of paper in half so that two distant points touch. Instead of traveling the entire length of the paper, you could simply pass through the fold, taking a shortcut. A warp drive would essentially create a similar fold in space-time, allowing a spacecraft to travel vast distances in a shorter amount of time without actually exceeding the speed of light within its local space-time bubble. The spacecraft would essentially be stationary within its warp bubble, while the bubble itself would move through space-time at speeds exceeding the speed of light. In 1994, Mexican physicist Miguel Alcubierre published a groundbreaking paper that sent ripples through the scientific community and reignited the dream of faster-than-light travel. Alcubierre's paper, titled The Warp Drive, Hyperfast Travel within General Relativity, proposed a theoretical framework for a warp drive that wouldn't violate the laws of physics as we currently understand them. Alcubierre's warp drive concept, known as the Alcubierre drive, relies on the idea of creating a warp bubble around a spacecraft. This bubble would compress space-time in front of the spacecraft and expand space-time behind it, essentially creating a local distortion in the fabric of reality. Imagine a surfer riding a wave. The surfer remains stationary relative to the wave, but the wave itself propels the surfer forward. Similarly, a spacecraft within an Alcubierre warp bubble would remain stationary relative to the bubble, while the bubble itself would surf through space-time at speeds exceeding the speed of light. Alcubierre's calculations showed that such a warp drive, while theoretically possible within the framework of general relativity, would require a peculiar ingredient: negative energy density or negative energy. Negative energy, a concept that sounds like it belongs more in the realm of science fiction than scientific reality, is a theoretical form of energy with peculiar properties. While we're familiar with positive energy, negative energy is thought to have the opposite effect, potentially causing space-time to contract or warp in unusual ways. The problem is that negative energy has never been directly observed in nature, and its existence remains a topic of intense debate among physicists. Harnessing these minuscule amounts of negative energy for something as ambitious as a warp drive would be a monumental challenge. If we can crack the code of negative energy, we may one day unlock the secrets to faster-than-light travel, expanding humanity's reach into the cosmos. In the annals of theoretical physics, Miguel Alcubierre's 1994 paper stands as a beacon of audacity and ingenuity. Alcubierre, a Mexican physicist with a penchant for pushing the boundaries of the possible, dared to tackle a question that had long tantalized science fiction writers and dreamers. Could we, even in theory, build a spacecraft capable of traveling faster than light? Alcubierre's solution, now known as the Alcubierre drive, was as elegant as it was mind-boggling. He realized that while Einstein's theory of special relativity prohibited objects from traveling faster than light through space-time, it didn't explicitly forbid space-time itself from moving faster than light. Imagine a flat sheet representing space-time. Now picture a tiny ant trying to traverse this sheet. The ant, constrained by the speed limit of its tiny legs, can only crawl so fast. But what if we could manipulate the sheet itself, creating a ripple that propels the ant forward at a much faster rate? This, in essence, is the principle behind the Alcubierre drive. Instead of propelling the spacecraft through space-time at superluminal speeds, Alcubierre proposed creating a warp bubble around the spacecraft, a localized distortion of space-time that would compress space in front of the spacecraft and expand space behind it. To grasp Alcubierre's proposal, we must confront general relativity. Space-time is a dynamic fabric warped by mass and energy. Imagine a bowling ball on a trampoline. The mass causes the fabric to sag. Massive objects create space-time distortions. Alcubierre proposed creating a dip in space-time. The spacecraft would ride this warp bubble. Think of it like surfing through space-time to reach distant stars. Alcubierre's equations, while mathematically sound, revealed a rather significant catch. Creating a warp bubble would require a peculiar ingredient, something called negative energy density, or negative energy for short. Negative energy is a theoretical form of energy with properties that seem counterintuitive, even paradoxical, in the context of our everyday experiences. While positive energy is associated with mass, gravity, and the expansion of the universe, negative energy is thought to have the opposite effect, potentially causing space-time to contract or warp in unusual ways. One way to visualize negative energy is to imagine a stretched rubber band. Stretching the rubber band increases its potential energy, representing positive energy. However, if we could somehow induce the rubber band to contract on its own, its potential energy would decrease, potentially reaching a negative value. The problem is that negative energy has never been directly observed in nature, and its existence remains a topic of intense debate among physicists. Some theories, like quantum field theory, suggest that negative energy densities might exist at extremely small scales, such as those found in the vacuum of space. However, harnessing these minuscule amounts of negative energy for something as ambitious as a warp drive would be a technological challenge of unprecedented proportions. Even if we could somehow solve the enigma of negative energy, the engineering challenges of building an Alcubierre warp drive would be nothing short of astronomical. Creating a stable warp bubble, one capable of safely transporting a spacecraft across vast interstellar distances, would require a level of technological sophistication far beyond our current capabilities. One of the primary challenges lies in the sheer amount of energy required to create and maintain a warp bubble. Calculations suggest that even a small warp bubble, one capable of transporting a spacecraft a few light years, would require an amount of energy equivalent to the mass energy of Jupiter, the largest planet in our solar system. Another challenge lies in the stability of the warp bubble itself. The slightest fluctuation or instability in the distribution of negative energy could cause the bubble to collapse, potentially with catastrophic consequences for the spacecraft and its occupants. And then there's the issue of radiation. Theoretical models suggest that the intense gravitational gradients at the edges of a warp bubble could generate deadly levels of Hawking radiation, a type of radiation emitted by black holes, which could fry the spacecraft and its crew in an instant. The most formidable obstacle standing in the way of warp drive technology is the elusive nature of negative energy. Alcubierre's warp drive concept hinges on the existence and manipulation of negative energy density. Positive energy is associated with mass and gravity, while negative energy could cause space-time to contract or warp. The problem is that negative energy has never been directly observed in nature. To create a warp bubble, we need vast amounts of negative energy, far exceeding current physics predictions. Even if we could solve the enigma of negative energy, the energy requirements for a warp bubble are astronomical. Calculations suggest a small warp bubble would need energy equivalent to Jupiter's mass energy. To put that into perspective, humanity's yearly energy use is 1 billion times smaller than a gram of matter. Harnessing such energy requires technologies far beyond our current capabilities. It would be like trying to boil the ocean with a campfire. The quest to manipulate gravity for faster-than-light travel is not without its risks. These forces could potentially alter the fabric of space-time in unpredictable ways. One concern is creating wormholes, theoretical tunnels through space-time. Their stability and safety are uncertain at best. Imagine a portal collapsing, trapping whatever's passing through it, or connecting to a region of intense radiation, unleashing havoc. Manipulating gravity could have unforeseen consequences for the universe. The dream of manipulating gravity to achieve faster-than-light travel, while still firmly rooted in the realm of theoretical physics, has ignited a spark of imagination in scientists and dreamers alike. The challenges are undeniably immense, demanding a level of scientific understanding and technological prowess that lies beyond our current grasp. Yet, the pursuit of knowledge, the relentless drive to explore the unknown, has always been humanity's greatest strength. While a warp drive capable of whisking us across the galaxy remains a distant aspiration, the quest to unravel the mysteries of gravity continues to yield valuable insights. Every experiment, every theoretical breakthrough brings us one step closer to understanding this fundamental force that shapes the cosmos. The quest for warp drive technology is not merely about finding a faster way to travel between stars, it's about pushing the boundaries of human ingenuity, challenging our assumptions about the nature of reality, and exploring the boundless possibilities hidden within the fabric of the universe. Just as Einstein's revolutionary theories of relativity shattered our Newtonian view of the cosmos, opening up a realm of black holes, wormholes, and warped spacetime, so too could future breakthroughs in gravity manipulation unlock technological marvels we can scarcely imagine today. Even if faster-than-light travel remains elusive, the pursuit of this dream has the potential to revolutionize our understanding of the universe and our place within it. The technologies and insights gained along the way could lead to breakthroughs in energy generation, propulsion systems, and our understanding of the fundamental laws of physics. Imagine harnessing the power of gravity to create artificial gravity fields, enabling us to explore the cosmos without the debilitating effects of prolonged weightlessness. Picture spacecraft propelled by the subtle curvature of space-time, gliding effortlessly between planets and stars. The pursuit of gravity manipulation could also lead to breakthroughs in our understanding of the early universe, black holes, and the nature of dark matter and dark energy, the mysterious substances that make up the vast majority of the universe's mass and energy. The universe is a vast and mysterious place, full of wonders waiting to be discovered. As we continue to explore the cosmos and delve deeper into the fundamental laws of physics, we may find that the seemingly impossible is merely a challenge waiting to be overcome. The dream of manipulating gravity for faster-than-light travel may be a distant goal, but it's a goal worth striving for it pushes us to reach beyond the limits of our current understanding and imagine a future where the stars themselves are within our grasp.